Welcome to the class of optical communication. Today we will discuss the topic of ray transmission theory in optical fiber communication, and my name is Himanshu Nagpal, assistant professor in AC department of AKGEC Kajeba. So today we will discuss about there are two types of transmission theory in the optical fiber communication. One is your ray transmission theory, another one is your waveguide transmission theory, wave theory transmission. In this ray theory transmission, we will consider that the light is traveling as a ray, and in wave theory transmission, in which we will consider the light is traveling as a wave in a waveguide. Now, the first of all we will discuss about the optical fiber cable, and the optical fiber cable is made up of what? Is made of dielectric waveguide, which is having a core and cladding material, and in which, if I say this is a optical fiber cable and inner one is known as the core and the outer one portion of the optical fiber cable is known as cladding. Clear? So if I talk about the refractive index, the refractive index of core is generally we represent it as N1, and the refractive index of cladding is generally we will represent it as N2. And when I say that it is an optical fiber cable, for the optical fiber cable, that the refractive index of core, it should be greater than the refractive index of cladding, and this is must for transmission of signal from in the optical fiber cable. That means that N1 should be greater than N2. Clear? So if I say this is a core, inner portion of this waveguide, which is in the form of cylinder, that is known as the N1, and the outer portion of the which will cover the core, that is known as a cladding, and it is having a refractive index of N2. Now optical fiber is what? Is a solid glass material surrounded by a cylindrical glass shell. This is core, this is a core which is surrounded by a cladding, and this core and cladding both are surrounded by the buffer coating, which protects the which is having a main role in protecting the core and cladding. The rod is the inner portion. The rod is called as a core, and which is made up of highly purified glass. Most of the light energy is confined into the core, means most of the signal or light energy is mainly travel in the core only. The glass shell, the glass shell is known as the cladding, which is surrounding the core. This cladding shields the optical field so as not to get transferred by the outer layer of the by the outer layers of the fiber. This cladding is an essential part of an optical fiber, because this cladding is generally having a main role in transmission of optical fiber cable, which will protect the core also, and also its refractive index having a role in transmission of optical fiber cable by the total internal reflection. This cladding is also surrounded by the buffer layer. These buffer layer have no role in propagation of light, but it provides the mechanical support to the glass fiber, and it also protects the glass fiber from the external damage. Now, for the light to propagate inside the optical fiber cable through total internal reflection, in which the basic principle for the ray transmission theorem, that is known as the total internal reflection, which is in the short form it is known as what we can say that it is TIR, that is a total internal reflection. This is a basic principle in the optical fiber cable for the transmission of signal, or you can say for the transmission of ray. That is a total internal reflection, and this total internal reflection takes place as what? Core cladding interface, in which we just have to have that N1 should be greater than N2 for performing the TIR. Clear? Now this silica fibers, the earlier we have discussed about the glass fiber, and now the fiber which is made up of silica, both core and cladding are of glass. Very pure SiO2 or fused quartz is used in making a silica fibers. The germanium phosphorus to increase the refractive index of the optical fiber cable. Boron and fluorine to decrease the refractive index of the cladding. The silica fiber are mainly used due to their low intrinsic absorption at wavelength of the operation. I will discuss about the what is the intrinsic absorption and the extrinsic absorption in the next lectures. And the other remaining impurities which will cause the attenuation and the scattering. We will discuss about the attenuation and the scattering in the next coming lectures. Now, what is the basic principle of transmission theory, transmission in optical fiber cable, which I have already told that the basic principle is what? That is a total internal reflection, in which in this total internal reflection we will discuss about the critical angle and we will discuss about the numerical aperture of the optical fiber cable. Clear? The basic theory of the basic laws of ray theory or transmission, that the in homogeneous material the light rays are straight lines and the light may be absorbed or reflected. Let's say if I say this we'll discuss here that the in this slide that is a total internal reflection, in which you will see that if I say this is an interface and this interface is what? Core cladding interface. Now this core cladding interface and this portion below this interface is core, if I say, and above this portion I'll say that is cladding, and this core has a refractive index that is equal to N1 and this cladding has a refractive index is equal to N2. Clear? Now the basic principles of the law of reflection states that when a ray transmit from one medium to another medium, the way the ray gets reflected, means the ray may get reflected from away from the normal or towards the normal. That depends on the what? That depends on the refractive index of one medium and the refractive index of another medium. If I say the ray transmit from lower refractive index to higher refractive index medium, higher refractive index, then the reflected ray will move towards the normal. Clear? But here we will see that if I say the refractive index has a material has a refractive index that is N1, which is greater than what? Refractive index of another medium, that is N2, and the ray is transmitted from higher refractive to lower refractive index, the ray will move away from the normal, means which is opposite to this one. This is the one of the laws of reflection, that reflection. Clear? Now if I say this is a normal, with normal to what? Normal to the core cladding, interface. And if I say now the ray, if I say the ray strike at the core cladding interface at an angle of phi 1, and the ray get reflected, not reflected, the ray get reflected at an angle of phi 2 from what? From the normal. Then phi 1, you can say that the phi 1 will be what? Phi 1 is less than the phi 2. Clear? Now, if I say, if I further increases the phi 1, if I further increases the phi 1, then the ray what? Then the ray will move away from the normal, and if I say the ray will get what? Will get away from the normal, which makes an angle of phi 2, that is equal to 90 degree, or you can say the ray will be reflected ray will be travel along the core cladding interface. Clear? So that incident angle is known as the critical angle. That incident phi 1 becomes what? Critical angle. Now, if I further increase the critical angle or incident angle, which will be what? Greater than the critical angle, then phi 2 will also get increases, and the ray which is earlier traveling along the core cladding interface, then the reflected ray will get reflected along in the same medium. Means if I further increase the phi 1 greater than phi c, then the ray, reflected ray, will get reflected towards the same medium, and here phi 1 becomes equal to here phi 2, means this phi is equal to this phi. Clear? So now the means the law of reflection will take place, means in which the angle of incident angle will become equal to the reflected angle, and this is the TIR, total internal reflection, in which if I say that if the incident angle is greater than the critical angle, then the reflected ray get reflected or reflected ray get back into the same medium, which makes a angle of same phi 1 as the incident angle. Now, according to Snell's law, in the law of reflection, which says that now, according to the laws, Snell's law of reflection, which states that the n1 multiply में sin phi 1 is equal to n2 into में sin phi 2. Clear? So sin phi 1 upon में sin phi 2 is equal to what? n2 by n1, where n1 is what? Refractive index of the first medium, and the another phi 1 is the angle of incident, and phi 2 is the angle of reflection, and the n2 is the refractive index of the second medium. Now, what is the critical angle? Critical angle, I have already told you from this figure also, that when the angle of reflection is 90 degree, which is normal to the what? Reflected ray is parallel, and which is 90 degree with respect to the normal, and the reflected ray is parallel to the interface between the two media, and at that time of incident angle is known as the critical angle, and in this case the incident is known as the critical angle. So using the Snell's law, I have already told you that sin phi 2 sin phi 1 upon में sin phi 2 is equal to what? n1 by n2, n2 by n1. No, according to the Snell's law, what? Let me erase this. According to Snell's law, sin phi 1 equal to n1 into में sin phi 1 equal to n2 into में sin phi 2. Now this phi 2, when this phi 2 becomes equal to 90 degree, then phi 1 will become equal to phi c. So you can say that the sin n1 into में sin phi c is equal to n2 into में sin 90 degree. It means that the phi c sin phi c is equal to the n2 by n1. As we know that sin 90 degree is equal to 1, so phi c will become, means the critical angle will become equal to what? Sin inverse of n2 by n1. So here phi c will become equal to sin inverse of n2 by n1. So if the angle of, now if I further increase the, from this figure I have already told you, if I further increase the incident angle which is slightly greater than the critical angle, then this ray which is earlier which is earlier to the, is parallel to the core cladding interface, now this ray will get reflected back into the same medium. So if I further increase the angle of incidence greater than the critical angle for a given setting, the resulting type of reflection is known as the total internal reflection. Means the wave, the reflected wave will get back into the same medium, or will get reflected back into the same medium. Clear? Now the next term we will discuss here, that is a acceptance angle. Now acceptance angle is the angle at which the reflection occurs is very crucial, because at this angle the ray will get coupled to the enter into the optical fiber cable, which will follow the principle of total internal reflection. Means this angle will decide whether the ray which is entering into the optical fiber will follow the principle of total internal reflection or not. Clear? Now if I say this one, this is the transmission of a light in perfect optical fiber cable. Now see, this is the, let's say this is the optical fiber cable, and this is a core, this is the core, and this is the one is the cladding. Now the ray gets enter into the optical fiber cable, and which is making an angle of phi at the core cladding interface, and this phi must be greater than what? Critical angle. So when this phi is greater than the critical angle, the ray will get reflected back into the same medium, which will follow the law of reflection. Means this phi 1 become equal to this phi, means angle of incidence will become equal to the angle of reflection. Means this phi 1 is equal to phi 1, or you can say, if I say this is phi, then this also becomes equal to phi. Similarly, this trend will follow, this ray will get reflected at this core cladding interface, which is making an angle of what? Incident angle, which is greater than the critical, and then this angle, this ray will also get reflected back into the same medium, and this here, the first phi will become equal to this phi, and this phi will become equal to this phi. So that is the total internal reflection. Here the angle of incident greater than critical angle, and at this core cladding interface also the incident angle, which is this making the critical, which is incident angle which is making this ray at the core cladding interface is greater than the critical. Then at this core cladding interface total internal reflection also will take place. Similarly, at this core cladding interface total internal reflection will take place. Now see, this one is the basic principle of total internal reflection in the optical fiber cable. Now next one is the, now here we will discuss the, now in the next topic we will discuss the angle which is making at the entry of the optical fiber cable. And when we will discuss about the angle which is making at the entry of the optical fiber cable, now we will discuss about the acceptance angle. Now see, let's say this is the start of the optical fiber cable, and this portion is cladding, and this innermost portion of the optical fiber cable is core. Now see this one. If I say this here is a LED source, if I say here is a LED source which is generating a light signal, and this light signal is enter into the optical fiber cable, and let's say this is a acceptance cone in 3-dimensional. If I say this is a 3-dimensional optical fiber cable, then this will make what? Cone. And this cone, it will be known as was acceptance cone. Now if I say this, the ray, this LED source is generating a light at this. So the rays which is enter into the light which is enter into the between this medium, between this cone is entering into the optical, then that ray will only follow the total reflection, total internal reflection. The ray which is outside this acceptance cone, the light which is entering into the optical fiber cable which is outside the optical fiber cone, that is the ray B, let's say, then this ray will not follow the total internal reflection, and so this is known as the acceptance cone. Or if I further now see this one again, I'll just describe this. Let's say this is a light source, light ray A, and this is a ray light B. Now this, if I say this ray light A which is entering into the optical fiber cable, and this is between the range of what? Acceptance cone, that is theta A. The ray which is entering into the optical fiber cable within the acceptance cone area or within acceptance angle, this is acceptance angle, then these rays will all these rays will follow what? Will follow the total internal reflection. Clear? Now the ray which is beyond this acceptance cone or acceptance angle, acceptance cone is the 3-dimensional figure which is making a, this one is the cone, and acceptance angle is the angle which is making from the core cladding interface to the angle of entry at what air core interface. If this, let's say this is theta A which is a maximum trigger, if I say this phi 2, this is theta 2, if this theta 2 is greater than the theta 1, then this ray will enter into the optical fiber cable, but it is making a entry into optical fiber beyond the acceptance cone. Then this ray, let's say this is ray B, then this ray will not follow the total internal reflection, means this ray which is entering, which when it will enter into the optical fiber cable and it makes an angle which is not greater than the critical angle, then this ray will not perform the total internal reflection, and this ray will get penetrated into the cladding, and when it is get penetrated into the cladding, then this ray will what? Will eventually lost into the cladding only. Clear? And this ray will not perform the total internal reflection. So the only rays with a sufficiently shallow grazing angle, that is with an angle to the normal greater than the phi c at the core cladding interface, are transmitted by the total internal reflection, which I have already discussed. That is, not all rays entering at the optical fiber enter the fiber core will continue to be propagated with down its length. For example, from the figure you can see that I have already discussed that the meridional ray A enters the optical fiber cable at an angle of what? Theta A within a acceptance angle to the fiber axis. Then this ray is to be transmitted by the total internal reflection within a fiber core. Now see, for rays to be transmitted total internal reflection, then the all rays must be confined to the acceptance cone. Means the total internal reflection within a fiber core, they must be incident on a fiber core within a acceptance cone, which is defined by the conical half angle theta A, and this theta A is the maximum angle to the axis at which the light may enter into the optical fiber in order to propagate, and is often referred to as the acceptance angle. Now where the light ray B, which is making an angle greater than the acceptance angle, is reflected into the cladding and is eventually lost by the triangle and will not perform total internal reflection. Clear? So acceptance angle can be calculated. The formula for the acceptance angle, that is equal to sin theta A is equal to n1 upon में na into में sin pi by 2 minus में theta c, and the solid acceptance angle, which we'll discuss now. Here theta A is a two-dimensional figure. From the two-dimensional figure I can say that is a theta A, that is a acceptance angle. Now if I further increase that from the acceptance cone, the angle that is a solid acceptance angle, that is equal to what? Pi into में sin square theta A. Now next term is the numerical aperture. Numerical aperture is what? Is the optical fiber cable, is the light gathering ability of optical fiber cable. It means how much light can enter into the optical fiber cable, and that will perform the total internal reflection. Now say here same as when we discuss about the acceptance angle, then this ray, if I say this is a air and this is a cladding and this one is the optical fiber cable. Cladding and this one is the core. Now if I say this is a ray enter into the optical fiber cable making an angle of theta 1. If I say this theta 1 is within a range of acceptance cone or acceptance angle, then this ray will perform what? Total internal reflection. This ray will enter into the optical fiber cable at an angle of theta 2, and this will perform what? Total internal reflection. So from the figure you can see that theta 1 to the fiber axis which is less than the acceptance angle, then this ray enter into the optical fiber cable, and this fiber core has a refractive index that is n1, which is greater than the, which is slightly greater than the critical cladding refractive index, that is n naught, will become equal to sin theta 1 equal to n1 into my sin theta 2. Clear? Now see, you will see here that this one, if I use the Snell's law at this interface, you will see that the n naught into my sin theta 1 is equal to n2 into my n1. This is the core refractive index now, that is n1 into my sin theta 2. So you will see here that the sin theta 1 is equal to what? n1 upon my n2 into my sin theta 2. And this sin theta 2, when strikes this ray, which is an angle of, making an angle of theta 2, which strikes at this core cladding interface, and this definitely will what? Will make an angle of, incident angle, make an angle of greater than the critical angle, then this only ray will get reflected back into the same medium. So we'll see that is n naught into my sin theta 1, that is equal to n1 into my sin theta 2. Now considering the refractive index at the core interface, from the consider the triangle ABC, that is phi equal to pi minus, means consider this triangle, consider this triangle. This is a making of angle of theta 2, and this is what? This is phi, this is A, B, C, and this is what? Making an angle of 90 degree. So you can say that theta 2 is equal to what? 90 degree minus my phi C. Just put this value here, that is sin theta 1 is equal to n1 upon my n naught into my sin 90 degree minus my phi C, that is equal to n1 into my n naught equal to cos phi C, where n naught is equal to what? N naught is the refractive index of what? Refractive index of air, which is equal to 1. So here we will see that the sin theta 1 is equal to n1 into my cos phi C, cos phi. Clear? Now see further, n1 naught into my sin theta 1 equal to n1 into cos phi. Now just put this one, cos phi is equal to what? As we know that the trigonometric equation, that is sin square theta, that is plus cos square theta equals equal to 1. So I can say that the cos square theta is equal to what? Under root of 1 minus my sin square theta. So just put this value here. So just put the value of cos phi C. I'll start here, that sin theta 1 is equal to n1 into my cos phi C, and this n1 can be written as 1 minus my sin square phi C naught, phi sin square phi की whole power में 1/2. Now for the limiting case, if I say this theta 1 is at the maximum acceptance angle, then this theta 1 will become equal to what? Theta A. If I say this theta 1 is the maximum angle which is equal to what? As acceptance angle, then this also will perform what? Total internal reflection at this point. Then this phi will become equal to what? Further limiting, this phi become equal to what? Phi C. So you can say here that, then you can see that the, I'll written here that the sine theta A will become equal to what, n1 into में 1 minus में sin square phi c की whole power में 1/2. Clear? So this one I just further written here that the sin theta A will become equal to what, n1 into में 1 minus में sin square phi c the whole power में 1/2. Now I have already discussed that the critical angle is equal to what, critical angle equal to what, sin inverse of n2 by n1. So sin phi c will become equal to what, n2 by n1. So just put this value here. So you will see that the n1 into में 1 minus में n2 का स्क्वायर अपॉन में n1 का स्क्वायर की होल पावर में 1/2. On solving this one, you will get theta A, that is acceptance angle, is equal to what, will be equal to n1 का स्क्वायर माइनस में n2 का स्क्वायर की होल पावर में 1/2 का होल इनवर्स. और you can say that is sin theta A will become equal to n1 का स्क्वायर माइनस में n2 का होल स्क्वायर की पावर में 1/2. That is a acceptance angle, and this acceptance, this sin theta A, this sin theta A is known as the numerical aperture. That is equal to, numerical aperture is equal to n1 का स्क्वायर माइनस में n2 का स्क्वायर की होल पावर में 1/2. Clear? So sin theta A, the half acceptance angle, that is sin theta A is equal to sin inverse of n1 का स्क्वायर माइनस n2 का स्क्वायर होल की पावर 1/2. And this numerical aperture can also be written in terms of relative refractive index, that is delta, between the core and cladding. This delta is the relative refractive index, and this delta is equal to what, n1 का स्क्वायर माइनस में n2 का स्क्वायर की होल पावर में 2 n1 स्क्वायर. And this you can say that it is equal to numerical aperture का whole square upon में 2 into में n1 square. From the further, on putting this value, on getting in this value numerical aperture, that numerical aperture becomes equal to n1 into में 2 into में delta की power में 1/2. So delta can also, if I say the delta is very less than 1, then delta can also be written as the n1 minus में n2 upon में n1. So numerical aperture is the characteristic of any optical fiber cable which is having a ability of optical system to collect all the light incident on it in a one area, so that the light will get accepted by the optical fiber cable and will perform the total internal reflection. That is it is the light gathering ability of the fiber. Clear? So this parameter tells us that if we take an optical fiber cable, put it in front of the optical source, then how much the light is collected by the fiber from the source. The smaller the value of numerical aperture, means the smaller the value of angle of acceptance angle. So it means the smaller will be the light accepted by the optical fiber cable, which will perform what, total internal reflection. So today we have discussed about the ray transmission theory. In the ray transmission theory, we have discussed about the numerical aperture, a critical angle, and the acceptance angle. So the book which I have referred for preparing these slides, or books, the photograph which I have taken from the books, from the which photographs, diagrams which I've used in these slides are taken from this reference book, that is John M. Senior, Optical Fiber Communication Principle Practice by the John M. Senior, that is from the Pearson Education. Thank you.